Hi guys, this is a quick summary of chapter 8, which is our advanced theories of covalent bonding. So we've just learned a lot about Lewis structures and VSEPR, okay? So what we've learned about Lewis structures is that we use them as a simple model to determine our connectivity between the atoms that are forming a covalently bonded molecule, and looking at the total number of valence electrons in the molecule to help us work out whether the bonds are single, double, or triple. And then we can apply VSEPR theory to the Lewis structure that we've just drawn. So that is considering the electron pair geometry in 3D space so that we minimize the repulsions between the electrons in the bonds and the lone pairs. So remember, bonds have got electrons in, lone pairs are electrons are negatively charged, they're going to repel each other and spread out as far as they can from each other, okay? So what does that match up with what we did in chapter 6 about electronic configurations, where electrons actually are, right? They're all in these orbitals and we know their shapes, right? So the valence electrons forming these bonds are in these orbitals. We know what they look like, right? S orbitals are spherical, p orbitals are like dumbbells along the x, y, and z Cartesian axes. And then we've got the d orbitals, which are like double dumbbell shapes, and they are in planes aligned with, again, the x, y, and z Cartesian axes. So how are those electrons being shared to form covalent bonds and the orientations matching these molecular shapes we just learned from VSEPR? So one theory is valence bond theory, which imagines each atom forming a covalent bond has half-filled orbitals which are overlapping. And remember, an electron orbital is not like a solid thing, it's a three-dimensional area of electron density. There's a probability of finding an electron in there somewhere, so what we're doing is we're overlapping the wave functions of those electrons, right? So there's two ways that we can have that overlap between orbital, okay? One of them is directly along the axis where the bond is being formed, so conventionally we define that as the z-axis. So the electron density then is directly in between the nuclei of the two atoms forming the bond. We call that a sigma bond. We also form what's called pi bonds, which is where the electron density is mixing either above and below the line of the axis where that bond is being formed, or in front and behind that axis. So if we have a single bond is just a single sigma bond. Once we get into multiple bonds, a double bond is a sigma bond. You've always got to have like some electron density along the bonding axis, but there is also a pi bond, either in front and behind or above and below the axis. And similarly, a triple bond, again, is a sigma bond, but it has two pi bonds as well. So it will have both in front and behind and above and below the bonding axis. So the way we sort of tie these concepts together, the orbitals overlapping and the electron pair geometry from VSEPR, we use this idea of orbital hybridization. So these atomic orbitals mix to form hybrid orbitals. So usually we're talking about s and p orbitals mixing. Once we get to central atoms with expanded octet that can access their d orbitals, we sometimes mix some of the d orbitals in as well, okay? The idea of these hybrid orbitals are they are lower in energy than the atomic orbitals that they're coming from. And of course their orientations have to match the steric number predicted from VSEPR theory. So a quick reminder, steric number is, in layman's terms, the number of things attached to the central atom. So those things are either bonds or lone pairs on the central atom. You add those all up, that gives you the steric number, that gives you the electron pair geometry for VSEPR. So if we have a steric number of 2 from VSEPR, we know that is linear electron pair geometry, and how we would form the hybrid orbitals for that is mixing one s and one p orbital, which is an sp hybrid orbital. So in the same way, if we have a steric number of 3, which from VSEPR we know is trigonal planar electron pair geometry, we get there by mixing one s and two p orbitals to form an sp2 hybrid orbital. If we have the steric number of 4, that is tetrahedral electron pair geometry. So we form that by mixing 1s and 3 p orbitals, that's sp3 hybridization. And that's a nice one to think about in terms of, think about what methane looks like, for example. CH4, we know it's that tetrahedral shape from VSEPR. The bond angle is 109.5 degrees. We know it's carbon, so it's forming from overlap of p orbitals. This is where valence bond theory is really useful, right? Because you think of the shape of p orbitals, they're along the x, y, and z Cartesian axes, which are orthogonal to each other, all at 90 degrees. That does not match up with, we know the angle of a tetrahedron is 109.5 degrees, okay? So that's why you need to form these sp3 hybrid orbitals all in that 109.5 degree orientation to be able to align what we know about the atomic orbitals with what we know about the molecular shape from VSEPR. So once we get to central elements that can expand their octet, they can also include the d orbitals when they're forming hybrid orbitals. So this is when we get down to period 3, commonly from silicon, phosphorus, sulfur, chlorine. If our central atom can access the d orbitals, it can expand its octet, and you'll know that because you will have drawn the Lewis structure first. So if we have a steric number of 5 from VSEPR, that is our trigonal bipyramidal electron pair geometry, and the type of hybrid orbitals we'd be forming there would be sp3d by, you got it, mixing an s orbital, 3 p orbitals, and 1 d orbital. And similarly, once we get to the octahedral electron pair geometry, that's got a steric number of 6, and that's formed from sp3d2 hybridization. So that's a mixture of 1s, 3p, and 2 d orbitals. So a quick and easy trick for working out what the label is of your hybrid orbital is work out the steric number. The steric number is always the sum of the indices in the notation for your hybrid orbital, okay? So sp hybrid orbital, so s to the power of 1 plus p to the power of 1, 1 plus 1 is 2, that gives you a steric number of 2, right? sp2, s to the power of 1, p to the power of 2, 1 plus 2 is 3, gives you a steric number of 3, and so on and so forth, okay? So that's the quick and easy way to remember it. So then that leads us up to molecular orbital theory. So molecular orbital theory is a bit more of an advanced treatment of some of the ideas we come across in valence bond theory, where we are taking the wave functions of the atomic orbitals of the two atoms forming this covalent bond, and they are going to join together to form molecular orbitals. So in valence bond theory, these hybrid orbitals still are localized, they still belong to a specific atom that's forming the bond, but when we are talking about molecular orbital theory, these molecular orbitals belong to the molecule as a whole. This is called delocalization. So the way we deduce what molecular orbitals are formed is called linear combination of atomic orbitals. So we combine the wave functions of overlapping atomic orbitals, and there's two ways this can happen. They can either be in phase with each other, so you get constructive interference, and the kind of molecular orbital that forms from constructive interference has the majority of the electron density in between the positively charged nuclei of the atoms forming the bond, and we call this a bonding orbital. If you think about it, those negatively charged electrons are somewhere mostly in the region between the two positively charged nuclei, so those electrons are going to help hold the nuclei together. That's a bond, right? Holding the two atomic nuclei together. So these bonding orbitals are lower in energy than the atomic orbitals they came from. We call this that they are stabilized, okay? And on the other hand, when we combine our wave functions, the other way that can happen is that the wave functions are out of phase with each other, so they cause destructive interference. So destructive interference cancels out. That means there's a node in that molecular orbital, zero amplitude, right? So there can be no electron where you have a node, and that's in between the nuclei. So if there's no electron density in between the nuclei that are forming the bond, that is not going to mitigate the repulsion between those two positively charged nuclei. So it's going to make that antibonding orbital higher in energy than the atomic orbital that it came from, so it destabilizes the molecule, and we label this with an asterisk. Okay, so electrons will fill bonding and antibonding molecular orbitals, but just remember the bonding orbitals are lower in energy than the atomic orbitals they came from, and the antibonding orbitals are higher in energy than the atomic orbitals they came from. So when you're trying to work out what molecular orbitals are actually formed, you need to consider what atomic orbitals are mixing, okay? So if you mix 1s atomic orbitals from each atom forming the covalent bond, you end up with a sigma 1s bonding molecular orbital and a sigma asterisk or a sigma star, we commonly call it 1s antibonding molecular orbital. So again, we still use the same definition of sigma and pi bonds that we used in valence bond theory. The sigma bond is when electrons occupy a molecular orbital, which is formed from linear or end-to-end, if you prefer, overlap of atomic orbitals. So that's along the bonding axis. And in the same way as we could mix 1s atomic orbitals, we can mix 2s atomic orbitals, and we form a sigma 2s bonding molecular orbital and a sigma star 2s antibonding molecular orbital. So it gets a bit different when we get to the p orbitals, right? There's 3 degenerate p orbitals, px, py, pz. The electron densities aligned along the x, y, and z Cartesian axes, respectively. So generally, we label the z-axis as the bonding axis. So the pz atomic orbitals are the ones that are aligned along the bonding axis. These mix to form sigma and sigma star molecular orbitals, which form sigma bonds. And then the other 2 p orbitals, which in our definition would be the px and py atomic orbitals. They would be in front and behind and above and below the bonding axis, respectively. So they would form pi 2px, pi 2py, and pi star 2px and pi star 2py molecular orbitals, and these would be the molecular orbitals that form pi bonds. So a pi bond in terms of MO theory is when the electrons are occupying a molecular orbital which is formed from lateral or side-by-side overlap of atomic orbitals. So once you've worked out what molecular orbitals you end up with by combining the atomic orbitals of whichever atoms are combining to form the molecular bond, you can then just write an electronic configuration for the molecule, just like we've been doing for atoms. So what you do is you use notation for each molecular orbital which is being filled. You write it in parentheses and then use a superscript to say how many electrons are in it. So each molecular orbital can contain 2 electrons, just like a normal atomic orbital, and we follow the same rules as writing the electronic configuration of an atom, right? So we fill the lowest energy molecular orbitals first. Electrons are going to singly occupy degenerate molecular orbitals first, so you only need to start worrying about that when you get to the pi 2px and pi 2py, right? So they'll occupy those first before pairing up. We've got a slight difference in order for oxygen, diatomic oxygen and beyond. Once you get to Z above 7, then the orbitals fill sigma 2p, pi 2p, pi star 2p, then sigma star 2p. And then up to forming diatomic nitrogen for Z equals 7. The sequence is flipped around for those first 2. It's pi 2p, then sigma 2p, then pi star 2p, then sigma star 2p. So it's just like writing electronic configurations for atoms in terms of you can omit the completely filled inner molecular orbitals. We can also calculate the bond order, which is a measure of how many bonds there are holding the nuclei together. So a bond order of 1 would be a single bond, a bond order of 2 would be a double bond. If you have a bond order of 0, that's telling you there is no bond, that's telling you the molecule is unstable and does not form. So to calculate bond order, you take away the total number of electrons in antibonding orbitals from the sum of the total number of electrons in bonding orbitals, and you divide by 2. Remembering that the bonding molecular orbitals are lower in energy than the atomic orbitals they're derived from, so they are stabilizing the molecule, and the antibonding molecular orbitals are raised in energy, so they're destabilizing the molecule. We can also use MO diagrams to deduce whether a molecule is going to be diamagnetic or paramagnetic. And remember, paramagnetic substances have unpaired electrons, and so they're attracted to a magnetic field, and diamagnetic substances have no unpaired electrons, so they're repelled by a magnetic field. Okay, so it's a lot to take in, a lot of it's very visual, and this is the second time my dogs have barked by the time I get to the end of this video. They are really irritating, but very cute. So I'm going to leave it there, guys, and we'll be back in chapter 9 to talk about gases.